Hello everyone and welcome. My name is Pimpiman Pipisit and today we are diving into Edge AI, artificial intelligence on small devices. As a developer, you have probably seen the explosion of AI in cloud services, but what happens when we bring that intelligence directly onto the device? In this session, we will cover what Edge AI is and why it's a game changer. Technical example, the latest hardware and software stacks, implementation steps, and where the field is heading. Let's get started. Before we talk about Edge AI, let's first understand what edge computing means. Traditionally, when a device like your phone or a sensor collects data, it sends that data to a big, powerful computer in the cloud for processing. Edge computing means doing some or all of that processing right on the device itself or on a nearby local server, instead of sending everything to the cloud. This is called the edge because it's at the edge of the network, close to where the data is created. Edge AI is when we run artificial intelligence models, like those that recognize faces, objects, or voices, directly on these edge devices. So, instead of sending a photo on the cloud to find out if it contains a cat, your phone or camera can figure out by itself, instantly. This is different from traditional AI, where the device just collects data and sends it to the cloud for all the smart processing. Let's compare the two approaches. Cloud AI, the device sends data to the cloud, then cloud runs AI model and sends the result back to the device. But for Edge AI, device run AI model locally, gets result instantly, and no need to send data away. So to summarize what Edge AI is, Edge AI refers to deploying and running AI models directly on edge devices. These are resource-constrained devices like smartphones, microcontrollers, Raspberry Pis, or IoT sensors. Instead of sending raw data to a centralized cloud server for inference, the model runs locally, right where the data is generated. This approach leverages on device compute resources such as ARM CPU, embedded GPUs, or dedicated NPUs, or what we call neural processing units. For example, a TensorFlow-like model or image classification can run on a Raspberry Pi using its CPU, or even a Coral USB accelerator for hardware-accelerated inference. The key technical challenge is optimizing models to fit within the device's limited memory, compute, and power budgets, often requiring quantization, pruning, or even architecture redesign. So, from a technical perspective, Edge AI offers several critical advantages. Latency. Inference happens locally, so you avoid round-trip delay to the cloud. This is crucial for real-time applications like robotics, AR/VR, or autonomous vehicles, where milliseconds matter. Bandwidth. Only processed results, not raw sensor data, need to be sent over the network, reducing bandwidth usage and cost. For privacy and security, sensitive data like audio, video, or health metrics never leaves the device, reducing attack surfaces and compliance risks. Reliability. Edge AI system can function offline or in environments with intermittent connectivity, which is essential for industrial IoT or remote deployments. The last one is scalability. Offloading inference to the edge reduces cloud server load, making large-scale deployments more cost-effective. Now, let's look at some technical use cases. Here are 5 examples that we could really find these small devices in real world currently. The first one is smart cameras. Object detection model like YOLO V5 or MobileNet SSD run on embedded devices, triggering events or alerts without streaming video to the cloud. Next is voice assistants. Wake word detection using model like Porcupine or TensorFlow-like runs on device, so only relevant audio is sent for further processing. For wearables, time series models for anomaly detection or activity recognition run on microcontrollers using frameworks like TensorFlow Lite for microcontrollers. The next one is industrial IoT. Predictive maintenance models analyze vibration or temperature data on site using platforms like NVIDIA Jetson or even STM32 MCUs. The last one is smart home. Edge AI enables real-time gesture recognition or environmental monitoring, often using ESP32 or similar chips with optimized models. Now, let's look at how Edge AI is making a real impact in the world through some concrete case studies. In modern agriculture, edge devices equipped with cameras and sensors are deployed in fields to monitor crops. Using Edge AI, these devices can detect plant diseases, pests, or water stress in real time, right where the data is collected. This allows farmers to respond quickly, reduce pesticide use, and optimize irrigation, all without needing a constant internet connection. Wearable devices like smartwatches and fitness bands use Edge AI to continuously monitor heart rate or even predict falls. Since the data is processed locally, users get instant feedback and their sensitive health data stays private. For example, a smartwatch can alert a user to an abnormal heartbeat in real time, potentially saving lives. Retailers are using smart camera with Edge AI to analyze customer movement, count foot traffic, and monitor shelf stock. This data helps optimize store layouts, improve customer experience, and reduce out-of-stock situations, all without sending video feed to the cloud, which saves bandwidth and protects customer privacy. In smart cities, Edge AI is used in traffic cameras and sensors to detect congestion, accidents, or even identify available parking spots. Processing this data locally enables instant responses such as changing traffic light or alerting emergency services. These real-world examples show how Edge AI is already transforming industry, making systems faster, smarter, and more responsive, all while protecting privacy and reducing costs. The possibilities are expanding every day as technology advances. Edge AI is advancing rapidly both in hardware and software. For hardware, microcontrollers like STM32, ESP32, Arduino Nano 33, BLE Sense run quantized models with kilobytes of RAM. Single-board computers like Raspberry Pi 4, NVIDIA Jetson Nano, Google Coral Dev Board support more complex models and hardware acceleration. Smartphones we use Apple's Neural Engine and Google Edge TPU enable on-device AI in consumer devices. What about software and frameworks? Nowadays, TensorFlow Lite is really famous on converts and optimized model for mobile and embedded devices, support quantization and hardware delegates. PyTorch Mobile for deploying PyTorch models on Android and iOS. This one is also famous, the Edge Impulse, end-to-end platform for collecting data, training, and deploy models to microcontrollers and edge devices. The last one is OpenVINO, Intel's toolkit for optimizing and deploying models on Intel hardware. In the field of model optimization, we use quantization to reduce model size and inference time by converting weight from float 32 to in8 or uin8. Pruning removes redundant weights or neurons to shrink the model. Knowledge distillation trains a smaller student model to mimic a larger teacher model's outputs. Model architecture use lightweight models like MobileNet, SqueezeNet, or TinyML architectures designed for edge deployments. Let's walk through a typical Edge AI workflow for developers. First, we need data collection. Gather and pre-process data, often directly from the target device sensors. Model training. Train your model using standard frameworks like TensorFlow, PyTorch on a workstation or in the cloud. Model optimization. Apply quantization, pruning, or convert to a lightweight architecture. Use tools like TensorFlow Model Optimization Toolkits or ONNX Runtime. Model conversion: convert the model to a format suitable for your device. For example, .tf Lite for TensorFlow Lite or CRAs for microcontrollers. On the step of deployment, flash or upload the model to your device. Integrate with device firmware or app code using SDKs or API provided by the framework. The last step is inference and testing. Run inference on device, profile performance, latency, memory, and power, and iterate as needed. So for example, suppose you want to build a real-time person detector on a Raspberry Pi. You need to train a MobileNet SSD model for person detection, then quantize and convert to TensorFlow Lite. After that, you deploy to the Pi, optionally using a Coral USB accelerator for edge TPU support. And lastly, use OpenCV for camera input and post-processing. Now that we have explored the fundamentals and benefits of Edge AI, it's important to understand the real-world challenges and limitations you face as a developer. Let's break down the key technical hurdles. 1. Limited resources. Edge devices like microcontrollers or single-board computers have far less memory storage and processing power than cloud servers. For example, a Raspberry Pi 4 has only a few gigabytes of RAM, and many microcontrollers have just a few hundred kilobytes. This means you can't just deploy any AI model. You need to use lightweight architectures and optimize aggressively. 2. Power constraints. Many edge devices run on batteries or have strict power budgets. Running AI models, especially for tasks like real-time video analysis, can quickly drain power. Developers must balance model complexity with energy efficiency, sometimes using techniques like duty cycling or event-driven inference. 3. Model size and complexity. Not all AI models can be easily compressed to fit on edge devices. Techniques like quantization by reducing precision of weights and pruning by removing unnecessary connections help, but there's a trade-off. As you shrink the model, you may lose accuracy. Sometimes you need to redesign the model architecture entirely for the edge. 4. Deployments and updates. Managing and updating models across thousands of distributed devices is a logical challenge. You need robust deployment pipelines, version control, and sometimes over-the-air, or what we call OTA. Update mechanisms to ensure all devices are running the latest and most secure models. 5. Security. While Edge AI improves privacy by keeping data local, it also means that the device itself becomes a target as well. Attackers could try to extract model or tamper with data. Securing the device, encrypting models, and using secure boot are all important considerations. 6. Debugging and monitoring. It's much harder to debug and monitor models running on remote, resource-constrained devices compared to cloud environments. You may need to build custom logging, remote monitoring, or fallback mechanisms. Understanding these challenges is crucial for building robust, reliable, and secure Edge AI solutions. As you design your system, always consider these trade-offs and plan for them from the start. This is 2025, and Edge AI is still evolving quickly. So the current trends, there are proliferation of AI accelerators in consumer and industrial devices. There are also growth of tiny ML, running ML on microcontrollers with less than 1 megabyte RAM. Also, there is end-to-end platform like Edge Impulse that simplify data collection, training, and also deployment for edge devices. And for future trends, there are Federated Learning. Devices collaboratively trains model without sharing raw data, improving privacy and personalization. On device training, not just inference, but incremental learning on the edge. Energy efficient AI, research into ultra-low power models and hardware for battery-powered devices. And for edge-to-cloud synergy, hybrid system where edge devices handle real-time inference and the cloud manages heavy training and model updates. Applications: autonomous vehicle, AR/VR, smart cities, and robotics will increasingly rely on Edge AI for real-time, context-aware intelligence. To wrap up, Edge AI is transforming how we build intelligent systems, enabling real-time, private, and scalable AI on everything from microcontrollers to smartphones. As developers, we have powerful tools and frameworks to bring AI to the edge, but we must also consider the unique constraints and opportunities of these platforms. I encourage you to experiment. Try deploying a quantized model to a Raspberry Pi or build a tiny ML project on an Arduino. If you have questions or want to dive deeper, check out the resource link below or reach out to me directly. Thanks for watching and happy coding!